Hello everyone, my name is Nick Ganazzi and I'll be presenting the paper Application Level Autonomic Hardware to Predict and Preempt Software Attacks on Industrial Control Systems. This paper was published by Lee Lerner, Zane Franklin, William Bauman, and Cameron Patterson Bradley of the Department of Electrical and Computer Engineering at Virginia Tech and first presented at the 2014 44th Annual IEEE IFIP International Conference on Dependable Systems and Networks. In this presentation, I'll be reviewing a bit of background for the paper, including the current state of ICS security and vulnerabilities this paper tries to address. Next, I'll be introducing and reviewing the new security model outlined in the paper, what it is, what's required to make it work, and how it secures industrial control systems from attack. Lastly, I'll review the findings presented in the paper and go over some of the limitations of the proposed model. Let's review the current state of ICS security. Paramount to securing ICSs is physical security. This includes plant access security, including keycards and gates, as well as securing against internal and external threats such as industrial espionage agents and the random middle manager that opens the email with a virus attached. In some ways, this is the easiest to secure despite its importance. As we know, a programmable logic controller reads data in and changes the state of the system or plant to minimize deviation from the ideal. Since the sensor transmitting the data is seldom, if ever, connected directly to the PLC, this creates opportunities for attack. Currently, security for PLCs centers on the idea of zones of trust. Inner zones are trusted more and service the outer zones. Generally, software and hardware are found together in the inner zone. Because of this, all applications running on the hardware run in the same zone, meaning they can't reliably check each other since a penetration exposes all applications to attack. Most of the time, there's only one kernel, so the kernel must be all things to all apps. This can preclude security in the kernel as this may interfere with the primary task of running the applications. Any defenses must also receive regular updates, patches against zero-day attacks and other vulnerabilities. This is often done over a network for simplicity and can be used by attackers to gain access. Even with safe zones and separate kernels, vulnerabilities exist. A little bit on the current threats and issues faced by ICS security professionals. Threats come from everywhere and can include foreign governments like Russia, China, and even the US, militaries and extremist groups who all have large or even vast resource levels and sophistication. Online vulnerability brokerages enable small bad actors to access zero-day vulnerabilities and other tools for a price. Hackers face little to no threat of retaliation due to the difficulty in tracing the origin of an attack, as well as legal issues pursuing foreign threats. An example of such an attack is the suspected sabotage of a pipeline in Siberia in 1982 by, supposedly, a CIA-directed implantation of malware causing excessive gas pressure. The explosion had roughly 1/6 the power of the first atomic bomb. I want to take a bit and review SCADA systems, both because the paper uses them as an example of the level of security required in today's environment, and because I work for a public utility that makes use of one. Supervisory control and data acquisition, or SCADA systems, run much of our utility infrastructure, but has many vulnerabilities. Operation of these systems includes human-computer interaction and networked infrastructure, including PLCs. The result is security issues that are from both IT and hardware vectors. Insiders, maintenance ports, zero-day attacks, and even PC updates are all vulnerabilities for a SCADA system. The Stuxnet attack on the Iranian nuclear program's SCADA system shows that even an air gap is insufficient security in the face of modern attack methods. Stuxnet was delivered using an infected USB drive which crossed the air gap and delivered the worm. The paper introduces a new security model that proposes a method to deal with these security threats. Called Trust Enhancement of Critical Embedded Processes, or TSEP, it does not rely on any software layer for trust, uses configurable hardware, and uses the idea that PLCs will be controlled via system-on-chip industrial controller. From the abstract in the paper, we mitigate malicious software threats to industrial control systems by using application-specific configurable hardware to monitor and possibly override software operations in real time at the lowest I/O pin level of a system-on-chip platform containing a microcontroller augmented with configurable logic. The process specifications, stability preserving backup controller, and switchover logic are specified and formally verified as C code commonly used in control systems, but synthesized into hardware to resist software reconfiguration attacks. Let's review the basics of TCEP as presented before we get into specifics. TCEP is a dedicated platform for domain-specific applications. Its only job is to make sure that the plant is running as it is supposed to. The new generation of field programmable gate arrays are capable of running functions as software on hard or soft processors. TCEP exploits this flexibility to invert the software and hardware responsibilities. TCEP moves critical industrial control system functions to verified programmable logic controller hardware blocks for each PLC. These blocks cannot be modified by local or remote software, which is the basis for the security model. To the right, we see the TCEP design model. The white boxes show standard engineering plans common in industry, while the shaded boxes indicate the additions to the decision tree from TCEP. Note that for the most part, the additions from TCEP are about verification of decision-making points. How does TCEP work? By using pre-programmed models and guides that are used to verify commands. For prediction, the development models for the plant operations are retained and reused in deployment to programmatically monitor current conditions and predict future states. TCEP uses physical process models to have an operations guide at all times. Using predefined limits of operation, TCEP can determine when an attack may be happening and respond. TCEP also verifies. It verifies all input and output commands as a sanity check and switches to the backup controller if the environment goes outside either the predictive or predefined boundaries. What types of attacks does TCEP prevent? It can prevent a denial of service attack by implementing the backup controller when the regular controller is unreachable. A network intrusion or an inside operator where the model takes over if the commands are outside operational bounds. Note, this doesn't have to be malicious either. Human error that would cause the same damage as an attack would also be prevented. Let's look at a security model comparison. As you can see, this table shows how TCEP stacks up against current security models like that of a single software kernel and a model that includes a split kernel with a trust zone. I want to highlight in this table that TCEP addresses internal and external vulnerabilities that other security models do not, such as analysis of hardware monitors and shared hardware and software resources between safe and non-safe zones. Note that TCEP is focused on securing against internal vulnerabilities in a way the other two are not, though it also addresses external and authentication issues. These next few slides, I'll be going through the example presented in the paper of how TCEP might be implemented. Here you see a representation of how the various parts of the system are connected. The trusted zone is a discrete part of each programmable logic controller. The trusted zone is separate from the production controller and prediction units. The plant model and specification guards in the hardware monitor all inputs from the production controller and physical plant. The code for this experiment was written using C with from a C as an analysis framework. The production controller is the primary method of instructing the PLC to act. It sends and receives data through the input-output module, or IOM. It's the usual source of PLC commands and controls. It uses a real-time kernel, which manages both the controller and IOM, since in the real world, there are real-time requirements for operation. The hardware monitor and backup controller live as a separate, trusted unit in the PLC. production to backup transitions can be reversed, where the backup takes over, during performance degradation events, such as a denial of service attack. A built-in probation period ignores the production controller for a predefined number of cycles, regardless of plant state after an attack, to ensure the health of the system. We'll see that a little later. The ability to do this requires predefined boundaries for acceptable operations. A minimum threshold must be thought out ahead of time so that random noise or other innocuous transient events do not trigger the security model. The prediction unit contains a copy of the production controller and ICS models. The prediction unit has 4 modes of operation: save, restore, normal, and accelerate modes. Save saves the current state into memory. Restore restores the state from memory from the saved state. Normal operates the system for 1 cycle. Accelerate operates for a predefined number of cycles, so it's not dynamic. During accelerate, no saves or restores will occur. And there can only be 1 state per cycle, so you can't do a save and restore at the same time. The junction box connects the production controller, physical plant, prediction unit, and the hardware monitor. It scrutinizes data to and from the physical plant, ensuring that commands are within design limits. Watchdog timers measure response times and send alerts to the backup controller when necessary, such as when there's no response received. Formal analysis tools are incorporated into the high-level design flow to verify functional and security specifications by evaluating mathematical proofs of design code semantic properties. The framework enables collaboration between various static analysis techniques implemented as plugins which can share information. So how does the security fit in? The backup controller and the plant model are stored on chip inside the hardware monitor in the safe zone. Hacking or disrupting the I/O manager or production controller leads to the backup controller assuming command of operation once operational parameters exceed tolerance thresholds. Hacking the physical hardware or junction box requires access to the site, which is, ideally, the hardest form of penetration. The system is designed to detect anomalous operations as soon as possible and restore normalcy to the system. Here are some graphs showing first a baseline and then the effects that TCEP had on countering an attempted malware attack. With no countermeasures in place, the top graph shows the plant's output exceeding the safe limit of 3.2 in about 100 cycles. Plant behavior with the hardware monitor appears in the bottom graph. Without prediction, the plant's output approaches the acceptable limit at t equals 480 milliseconds before being corrected by the backup controller. With prediction, the hardware monitor proactively invokes the backup controller at t equals 280 milliseconds, thereby preventing the physical plant from reaching an unsafe state. This graph shows the plant's output with prediction and automatic resumption of the production controller. As in the previous graph, the prediction unit forecasts the future consequences of the malware, and the hardware monitor again preemptively switches to the backup controller at t equals 280 milliseconds. The hardware monitor's probation counter expires, and the production controller is reinstated when the malware ends at t equals 650 milliseconds. 200 milliseconds before this time, the physical plant model, and predicted plant state are found to be within specifications. The paper's authors note that mechanisms are being developed to manage transitions between controllers in order to avoid excessive overshoot caused by stale state information. Resource utilization. Although performance wasn't a consideration in the development of this project, the resource utilization numbers are interesting. The project used an ARM processor running at 667 MHz, and the other hardware ran at 140 MHz. Even though a cycle time was set of 1 millisecond, one iteration of the software took only 1.43 microseconds. Projecting that out gives the system the capacity to predict about 500 cycles into the future, though whether that's a sufficient time depends on the use of the plant. Limitations and issues. So TCEP does have some limitations. Some of the following are from the authors and some are my own observations. Cost of specialized hardware. New FPGAs can cost more than the value of the plant. The additional processing power required may preclude TCEP's use in smaller plants. Use of prediction and security features require well and precisely defined operating limits, resulting in a large upfront cost in time and manpower during implementation phase. Great care must be taken to prepare the models ahead of time or unintended operations will occur. Remote access is not possible by design, so in-person updates and maintenance are required, resulting in an additional cost. The purpose of this paper is to demonstrate security, not performance. Although it doesn't appear to be an issue, per the paper, this security model has not been implemented in the real world. It's unknown how TCEP will respond to real-world issues not present in the model, up to and including catastrophic failure of part of the plant. The biggest issue I see with the model is that if TCEP checks everything incoming and outgoing and overrides when it thinks something is amiss, it's effectively autonomous and uncontrollable from the operations room. Conclusions. To quote the paper's authors, existing approaches to control system security add generic hardware or software layers to help isolate and secure applications. We instead use rigorous verification of application-specific hardware to counter software reconfigure attacks on critical processes, accomplished through the non-standard use of existing languages, tools, platforms, process specifications, and models. Non-standard use of these things may introduce unknowable security vulnerabilities at a later time, but the non-standard use of these things are also a very interesting exercise as a thought exercise in overcoming the current security limitations of the technology stack. Thank you.